Hey everyone, great to have you here. Some of you may have already noticed it. Cinnamon is out.
Cinnamon is our framework for TwinCAT 3. The framework follows object-oriented programming approaches and is fully open source. To help you understand how it works and how you can use it, we have uploaded an example project for you on GitHub.
You can find the link to the project, as well as to the framework itself, the Cinnamon documentation, and blog posts in the video description. So let's get started. In this project, we program several stations for the following scenario. Somewhere in the depths of outer space, a factory is floating around where cupcakes are produced on a small production line. The production line works as follows. At the beginning, there is a supplier that provides cupcake blanks. In front of the supplier, there is a light barrier. A small transport flying saucer flies towards the supplier and passes through the light barrier. When the sensor is triggered, a cupcake blank is spawned out of nowhere and lands on the transport flying saucer. The flying saucer transports the cupcake blank and stops at another light barrier. This light barrier activates a handling portal. If the portal is not occupied, it moves toward the flying saucer and picks up the cupcake. During transport, the portal gripper rotates the cupcake together with its plate by 45 degrees. Once the destination is reached, the cupcake is handed over to another flying saucer. When the cupcake is placed onto the flying saucer, it passes another light barrier. This opens an oven door, and the cupcake enters the oven. After baking, the cupcake is transported back by the flying saucer to another light barrier. There, the flying saucer requests handling, and a robot arrives to bring the cupcake to the next station. If the robot is still occupied with a previous cupcake, it has to wait until it has handed over its current cupcake to the next station. This behavior applies to all processes in the factory. The cupcake is then transported by the handling robot to a rotary table. The turntable has 4 sensors that indicate the current position of a cupcake and which positions on the turntable are occupied. Drop-off is the starting position where the cupcake is placed. The next position is glazing, where the cupcake is glazed. Position 3 is topping, where the cupcake receives its topping. The final station is exit, from where the cupcake is transferred onto a conveyor belt by a pusher. The turntable rotates whenever a new cupcake is delivered and there is enough space on the conveyor belt for another cupcake. All stations must also have completed their processes before the system continues. The cupcake now enters a conveyor belt. There are 3 light barriers along the belt. The third light barrier has the following function. When a cupcake passes it, a stopper is raised in front of the second light barrier. This prevents the following cupcakes from moving forward and avoids congestion at the next station. If the space on the conveyor belt between the first 2 light barriers is occupied, meaning both sensors are blocked by cupcakes, the turntable must wait before placing another cupcake onto the conveyor. This is the buffer section. Once the first light barrier is free again, another cupcake may follow. After a cupcake has passed all 3 light barriers, it reaches an image recognition station. Here, it passes another light barrier that activates a stopper for the vision system. The station identifies the type of cupcake by taking an image of the cupcake and sends image data and size to the PLC. Based on this information, one of 3 lift transfer units in the next section of the line is activated. Strawberry cupcakes are catapulted to a dinosaur. Chocolate cupcakes are sent to crocodile number 2. Vanilla cupcakes are sent to crocodile number 1. Burnt cupcakes are transported directly to the end of the conveyor and disposed of. The lift transfer units that are not required remain in the lower position, allowing the cupcake to pass. The required lift transfer unit is already positioned in the center. The cupcake stops, the sensor of the lift transfer unit is triggered, and the unit lifts the cupcake upward. From there, it is either transferred to a crocodile, disposed of, or catapulted to a dinosaur. To help you follow the project more easily,
the transport flying saucers are drives. The light barriers are sensors. The portal has 4 axes, X, Y, Z, and a rotational axis. The portal gripper is a cylinder, as is the oven door. The robot has 2 drives, one for Y and one for Z. The turntable is a drive, and above each of its 4 positions drop-off, glazing, topping, and exit there is a sensor indicating whether the station is occupied. The glazing and topping stations consist of a simple drive and a pusher. The exit station uses a cylinder. The conveyor belts are simple drives. The stoppers are cylinders. The transfer units are lift transfer units. Now you know the sophisticated production line behind our example project, and you are familiar with the individual stations. Like any automation project, our cupcake factory can be represented as a tree. Encapsulation of components is key here. We break our stations down into smaller and smaller components until we reach the hardware level. In our project, we use the hierarchical composition pattern to distribute the current operating mode through the tree to every node. Let's have a look at our tree.
Our root node represents the entire station. The subsequent nodes are children of the station. We divide into the following nodes: supply, baking, glazing, queue, and distribution. Within these nodes, we implement the process logic in the program. The child nodes of supply are flying saucer, truck sensor, robot sensor, portal robot, portal gripper. As you know, the portal has 4 axes. These axes are modeled as individual child nodes of the portal. The child nodes of baking are flying saucer, handling, handling gripper, oven door, drop-off sensor. Handling itself has 2 child nodes: axis Y, axis Z. The child nodes of glazing are turntable, drop-off nest sensor, exit nest sensor, toppings nest sensor, glazing nest sensor, pusher, cream brush, toppings dropper. The queue node has 4 child nodes: conveyor, stopper, entry sensor, stopper sensor. Distribution contains 9 child nodes: main conveyor, entry sensor, camera exit stopper, camera, camera blocked sensor, exit sensor. Next 3 branching units: Croco 1, Croco 2, and Catapult. Each of them has 3 child nodes: Croco 1 sensor, Croco 1 conveyor, Croco 1 LTU, Croco 2 sensor, Croco 2 conveyor, Croco 2 LTU, Catapult 2 sensor, Catapult conveyor, and Catapult LTU. This is our beautiful tree.
Now we open the example project and take a look at the main. At first glance, the main looks quite empty. This is because the call hierarchy is handled by Cinnamon. We start with the station unit. The 0 after the station unit indicates that this is the first level of the tree and therefore the root node. It inherits from the AbstractCyclicNode class of the CNM OpModeHandler library, because it does not contain any process logic. Here, supply, baking, glazing, queue, and distribution are declared. They are all initialized with a this. This way, each unit automatically receives the station as its parent node and registers itself as a child node in the tree. Next, we take a look at the supply unit. The supply unit is a single machine section with its own logic and therefore inherits from the abstract class AbstractModeNode. A quick look at the tree shows that all nodes on this level contain process logic and inherit from AbstractModeNode. This allows us to encapsulate different machine parts and clearly separate their workflows. The difference between AbstractModeNode and AbstractCyclicNode is that AbstractCyclicNode only performs monitoring by default, through its run method, which is called cyclically. In contrast, AbstractModeNode provides several methods for different operating modes, such as automatic operation, homing, and manual operation. Additional modes can be added as needed, and derived classes are required to implement the appropriate logic. Back in the supply unit, there are additional subcomponents, all initialized with a pointer to the parent. These include the portal, flying saucer, truck sensor, robot sensor, and portal gripper. Next, we take a look at the portal. The portal controls no process logic and therefore inherits from AbstractCyclicNode. It has a run method, but no mode logic. The same applies to the units declared inside the portal, they also extend AbstractCyclicNode. Now back to the main, where we find a few more important elements. First, the handler, which is our OpModeHandler, a ready-made class from the Cinnamon library. We assign the station unit as root node and mySafety as safety component. The OpModeHandler calls the root node, which then recursively calls all child nodes, no matter how deep the structure is. This results in a clean separation of logic and hardware, a clear structure, and reproducible behavior. The safety component inherits from an abstract class called AbstractSafetyReleaseDistributor. In the getter of the abstract property safety is OK, the conditions are defined that must be fulfilled for safety to be considered OK, return true. In our example project, the only relevant condition is an emergency stop. All elements for which the safety is relevant can subscribe to it. The OpModeHandler does this automatically when it is linked to the safety component. Finally, in the main, we also find the HMI unit, another class from our library, CNM OpModeHandler.baseHMI. This class is a concrete HMI handler implementation for the mandatory operating modes automatic, homing, and manual, and it also manages alarms and messages. In the declaration section of the main, the safety, the HMI, and the handler are executed. Now let's start our project. We open the HMI project. To run the project, we have to assign a project path, in our case main.hmi. We click on our little green button and let the HMI build itself. Even if no logic has been implemented, it is already possible to create an HMI project and configure the root node path for the Cinnamon server extension. As soon as the PLC project is downloaded and started, the HMI server retrieves the tree structure. When we compare the tree we drew at the beginning with the HMI, we can see it node by node. With this image, we now conclude our first video in the series, in which we talk about Cinnamon and our example project. In the second part, we'll go into more detail. If you don't want to miss that, subscribe to our channel and hit the bell. Until then, have fun exploring the framework. You'll find all the links to Cinnamon in the description. Bye.
Bye.